Last time we ended on this definition, we said a matrix P in Rn by n, so square matrices, is positive definite if for all x in the space Rn, x transpose times P times x is greater than or equal to 0. And the only time is actually equal to 0 if the vector x is equal to 0 itself. So this is an if and only if statement right here. And I want to give you some examples of positive definite matrices. So one easy example is a diagonal matrix with positive entries on the diagonal. So something like 3, 0, 0, 0, 5, 0, 0, 0, 1. So nothing negative or 0 here. And this is a 3 by 3 example. But of course you could do like a 4 by 4, 5 by 5, as long as what's on the diagonal is positive. How can we show that this is positive definite? Well, what you want to do, you see that this is a 3 by 3 example. So looking back at the definition, we're looking for vectors that are in R3, and we want to show that for every vector in R3, if you multiply the vector by this matrix and then multiply what you get by the transpose of that vector, you get something that's greater than or equal to 0. And how you can show that is you only really have to check it on the basis of R3. So you choose a basis and you show that this works because any other vector is a linear combination of those basis vectors, and you can take a linear combination. If you're multiplying, you can take the scalar that's in front and move it out, and then you can separate the sums of matrices. So just checking it on the basis vectors is enough. So let's do that. So a basis for R3 is E1, E2, E3. So let's check it on this basis. So if I take 3, 0, 0, 0, 5, 0, 0, 0, 1 and multiply it by 1, 0, 0 in the back and then 1, 0, 0 transpose in the front, what do I get? Well, I'm going to multiply these first. You see that you get 3, 0, 0. And then multiply these two together, you just get 3. And then if you multiply this matrix by E2, you'll get 0, 5, 0, and then you're going to multiply by E2 here. So let me do that one so you get another example of this. So if I change this to 0, 1, 0, 0, 1, 0, you're going to get 5. And then if you do it with E3, you should get 1. So you can see that for all the basis elements, you get something that's greater than or equal to 0. That was the definition of positive definite. It has to be greater than or equal to 0. And you also need to check that the only thing that works when you get, how you can get 0 is the 0 vector itself. So because we checked it for the basis, you can see that any other vector would be a linear combination of the basis vectors. So the only way to actually get 0 is if you put 0 in front of all of the basis vectors. And so there's no way to do it other than for the 0 vector itself. It'll always work for the 0 vector, because if you put 0, 0, 0 here in the transpose, you'll see that a matrix times a 0 vector is a 0 vector. So this is actually just going to be equal to 0. But yeah, anything else won't work. So if it works for these three, then you're good. You don't have to check anything else. So other examples of positive definite matrices, they don't have to be diagonal. You can have things that are not diagonal, and you can in fact have things with negatives in it. So let me give you another example. We're going to do a 2 by 2 matrix. Let's say we have the matrix P equal to 3, 1, negative 1, 1. I claim that this is positive definite. Well, let's see. A basis for R2 is E1 and E2. So this is a basis. And let's see what happens when we multiply this matrix by E1 and E2, and then also by the transpose. So 3, 1, negative 1, 1. If I put 1, 0 in the back and then 1, 0 transpose in the front, this is, well, if you multiply these two together first, you get 3, negative 1, but then multiply these two together and you just get 3. So it worked on that basis vector. Now try with the other basis vector. Well, the other basis vector is 0, 1, 0, 1 here. Multiply these two together and you get 1, because 3 times 0, 1 plus, 1 times 1, and then 1, and then multiply these, you get 1. So it worked on the basis vector, so this is a positive definite matrix. Let me show you something that's not positive definite. And this is actually a matrix that had zeros on the diagonal. So let's say 0, 1, 1, 0. Now, it doesn't have any negatives. So you got to be careful with this positive definite. When you see the word positive, you would think like maybe 0 or bigger for the entries, but actually here's a matrix with no negatives and it doesn't work. Let me show you. So if I apply this to 1, 0, and put 1, 0 in the front, what do I get? Let's multiply these two together. You get 0 here, and then a 1 here, and then take the dot product, and you get 0. And the reason this is not positive definite is because remember that in the definition, the only time you get 0 is if the vector x itself is the 0 vector. And you can see that when I plugged in a basis element, I got 0, and so that the vector x doesn't have to be the 0, just the 0 vector. And that was one part of the definition, so it's not positive definite. So there's lots of matrices out there that are positive definite. The easiest thing is things that are diagonal matrices, like the identity, diagonal matrix with positive diagonal entries. And there's a lot of strange ones as well. But why we're introducing positive definite matrices, I don't expect you to memorize what it is. I just wanted you to know all the forms the inner product could take on Rn. So now that we have an idea of what a positive definite matrix is, I'm going to tell you that for V equal to Rn and X and Y and V, all inner products on Rn take the form X transpose times P times Y, where P is positive is a positive definite n by n matrix. So if you want more examples of inner products on Rn other than just X transpose Y, here is an example. Just find a positive definite matrix and take X transpose and then multiply by Y, but also put this positive definite matrix in the middle. In fact, one of the examples in the book they give you is for a matrix that's diagonal. They kind of say it in a different way. They say you can say if W is a vector in Rn with positive entries, then an inner product on Rn will look like this. X with Y is equal to, I think they use, they say the sum, I is 1 to n, of xi, wi, xi, wi, yi, just like this. And the reason that works is because you can think of, so you have this vector x, which is x1 through xn. Y is y1 through yn. And z, not z, w. W is w1 through wn. And what you're doing is you're just multiplying x1 with y1 with w1. But you could also think of it as X transpose times this matrix W1, W2, Wn times the matrix Y. Because what happens here is everything in Y, so the first entry will get this W1 and the second entry will get the W2 and so on. And then you're taking X transpose, which is just the dot product of this matrix X, which will now be W1, Y1, W2, Y2, and so on. So you'll actually get this. So they didn't want to talk about positive definite matrices. They wanted to give you an example of an inner product on Rn, and is actually using positive definite matrices. They just found another way to explain it. But yeah, all inner products on Rn will take this form. Okay, let's talk about different vector spaces. So let's say we have the vector space of m by n matrices. So we can define a inner product on these matrices. We could say that the inner product of A and B is equal to the sum. Now we're assuming that A is an m by n matrix and it has entries aij, and B is also a m by n matrix and the entries look like this, where I and j, I runs from 1 to m and j runs from 1 to n. And we could just take the aijth entry and multiply it by the bijth entry, and that will be an inner product on the vector space Rm times n. So we're just looking at some examples. Here's another example. We're actually going to prove that this one is an inner product. So we have V is the continuous function continuous functions on the interval AB. And we're going to define the inner products for any two functions in your vector space as the integral from A to B of these two functions multiplied together. And I claim that this is an inner product. So inner product space is just a vector space. Now remember, vector spaces don't have any multiplication defined on it other than scalar multiplication. We can multiply scalars, but there's no such thing as multiplying vectors together in a vector space. But here we're actually defining a way to like multiply two vectors together, and it has to satisfy these three conditions. And when you have this mapping here, this inner product, then it's called an inner product space. So it's a vector space plus this additional product. Okay, so I'm saying that if we take this vector space and we define a product like this, this is actually an inner product. So how can we check it? We need to show, well, obviously, we need to make sure that we're taking two things in the vector space and assigning a real number. You can see that you have two vectors in your vector space, and an integral, a definite integral gives you a real number. So that's fine, but you also need to check that when you take the inner product of a function with itself, you are greater than or equal to 0, and it's actually equal to 0 if and only if the function itself is 0. So that's one thing you have to check. You need to check that if you take the inner product of two things, f and g, then it's symmetric. And then you also need to check that if you have a scalar times f plus another scalar times g and then another function, let's say h, then you can take those scalars out, and you can also take out this addition. So it's linear. These are actually probably the easiest to check, and then maybe these take a little more thinking. So how can we check it? Let's start with this one. So I'm going to do this one first. Here's the definition. The inner product of f with g is the integral from a to b of f times g times dx. Okay, so then what would the inner product of g with f be? Let's write it, I guess we can do it in green. The inner product of g with f is the integral from a to b of, well, it says here's fx with f, so it's going to be g of x times f of x times d of x. That's just following this rule, f first, then g. So here I have g first and then f. So we can multiply f times g is the same thing as g times f. So this is obviously true. Just switching the order of the f and the g doesn't matter when we take the integral. So this is obvious. Okay. What about the third? Let's erase this so we have some room. How do we check this one? Let's move it up. Well, just use the definition and see if you get this. So this is equal to the integral from a to b of alpha of f plus beta g times x times h of x dx. Because I take the first thing, that's a function of x, so I wrote it as a function of x, times the second thing, and I put it here. And now you know properties of functions. You can distribute this h of x to both of these guys, and then you can also take scalars real numbers outside of an integral. So this is alpha times the integral from a to b of f of x hx dx plus beta, the integral from a to b of g of x h of x dx. But then this is precisely this, and this piece is equal to this. So that's all you have to check. How about this actually the first condition of an inner product? How do I check that? So first I want to just talk about what the definition of a definite integral is, right? So these are functions of one variable. So if I have a function, let's say x cubed, and let's say a, b, because these are continuous functions on this interval, and we can choose an interval. So I'm just going to say that this is a and this is b. What does it mean to take the inner product of a function with itself? So following the definition, this is equal to the definite integral from a to b of fx times f of x dx. But this is a function squared. So this is from a to b of f squared of x dx. So for example, if we had x cubed, if I squared this function, well, if you square something, all of the values of that function on this interval, it looks something like that. It's the negatives are squared, so they're flipped to the positive, and it's actually a little bit skinnier than the original one because we're squaring them. So, and then the definite integral is the area under the curve, right? And so the only time the area under a curve is negative is if, it's below the x-axis. So you would add this part up with this one, and that's going to be a positive area. So the inner product of a function with itself is always going to be greater than or equal to 0. And you can see that it's actually only going to be equal to 0. Well, it's the area under a curve, and the only time it's equal to 0. This is a continuous function, keep that in mind. So the only time the area under the curve is 0 is if the curve is actually the 0 line,